Hello everybody, welcome to another video lesson. In this lesson we're going over graphing rational functions. We're going to do a lot of graphing today, and we're going to identify vertical, horizontal, as well as oblique asymptotes, which we also call slant asymptotes. So let's go ahead and get into our concepts. What is a rational function? A function in the form of fx is equal to ax over bx, where ax and bx are both polynomial functions themselves. Okay, so we now don't just have like 1 over a of x like we had for our reciprocal functions. We now have polynomial functions on the top and bottom of our function here in the numerator and denominator. All right, we have vertical asymptotes where our denominator is equal to 0, because we know our denominator cannot equal 0. And horizontal asymptotes, we have a few different situations here. All right, if the degree of A is greater than the degree of B, okay, so if the degree of my numerator is greater than the degree of my denominator, we have no horizontal asymptote. So here we can see the graph of x squared over x minus 1. We see we don't have a horizontal asymptote. Again, horizontal asymptote is showing us end behavior. Okay, so what's happening as x is going off into infinity in both directions. Okay. Now, if the degree of my numerator, a in this instance, is less than the degree of b, or my denominator, then our horizontal asymptote is going to be at f of x is equal to 0. Okay, so y equals 0. So if we have f of x here is 1 over x squared minus 9. We see that the denominator's degree is 2, the numerator is going to be 0, and so we have a horizontal asymptote here at the x-axis. Right? Now, if the degree of A is equal to the degree of B, okay, then our horizontal asymptote is going to be at f of x is equal to the lead coefficient of A over the lead coefficient of B. So here I've got 8x squared over 4x squared minus 9. So we can see here that my 8 over 4 is going to be my horizontal asymptote here. 8 over 4 reduces to 2, and we can see 1, 2. We can see we have a horizontal asymptote here at 2. Okay? So the lead coefficients will determine the horizontal asymptote if the degree of the numerator and denominator are the same, if they're equal to each other. Now, one last instance here, one last situation. If the degree of A, or my numerator, is exactly 1 greater than the degree of my denominator, then our horizontal asymptote is going to be the quotient of our function here. Right? So it's going to actually be ax over bx. So here I brought back up our x squared over x minus 1. So in order to find the oblique or slant asymptote here, because we can see as x goes into infinity and negative infinity, there is an asymptote here. It's just at an angle. It is not directly horizontal or directly vertical. It's going to be at an angle, which is why we call these slant asymptotes as well as oblique asymptotes. Okay. Oh, so this should be this should not be horizontal asymptote. This would be a slant asymptote, otherwise known as an oblique asymptote. So in order to find that, we got to take the quotient of my numerator and my denominator, which we've done here with long division. And I don't care when I do this. I do not care about my remainder. All right, my remainder equals, I don't know. I don't care. That's supposed to be a question mark. I don't care what the remainder is. All I need is the linear function that I get as my quotient. Okay, without the remainder. Don't care about that remainder. So here my horizontal asymptote would be f of x is equal to x plus 1. And if I go ahead and put that in, we can see, yes, I've got this point, or I've got my y-intercept at 1, and we have a slope of 1. This is going to be x plus 1 for my slant asymptote. All right, one more concept. The point discontinuities are what we're going to look at as well in this lesson. A discontinuity are just areas in a graph that are not continued or connected to each other. So remember we talked about if we have if you are drawing a continuous graph on an interval, when I put my pen down and I start to draw, okay, I don't have to lift up my pen. All right, the whole time I don't have to lift up my pen. But if I have a point discontinuity, then that is a point where our function is going to be undefined, and we see that as a hole in our graph. All right, so if I have f of x is equal to a of x over b of x, and if I factor a of x and b of x, and they both have this factor here, if I rewrite my function in factored form, if I have the same factor in the numerator as I have in the denominator, we can see that these kind of cancel out, right? Those are going to cancel out, and that is going to yield a point discontinuity at x equals c, all right? And that is at x equals c because this is minus c. If this was plus c, our point discontinuity would be at x equals negative c. So really we just set this equal to 0 and solve, and that is going to be our point discontinuity from that factor. All right? We also call these removable discontinuities as well, because it's like, if I look at my graph, it's almost like we removed this point here from our graph. Okay, so again, this looks continuous until we hit x is equal to c, and now we have this hole in the graph, and then we can keep going. Okay, so that is what a point discontinuity looks like on a graph. All right, let's take a look at just a few examples here. Okay, I've got x to the third over x plus 1. So we have a rational function here. First thing we're going to do is factor, and I really can't factor this anymore. This is as factors as it's going to get, so we'll just leave it as is. Now let's go ahead and identify our asymptotes. We're going to start with our vertical asymptote by setting the denominator equal to 0 and solving for x. So I'm going to get x is equal to -1 for my vertical asymptote. Now let's go ahead and identify horizontal asymptotes. Well, the degree of my numerator is 3. The degree of my denominator is 1. 3 is greater than 1, so we have no horizontal asymptotes. Okay, and 3 is greater than 1, but by more than 1. Okay, so it is 2 greater than 1, right? So I know we don't have any slant asymptotes as well. So when you start to graph these, always graph your asymptotes first. Okay, and then we can kind of see from there, when we build our table, where we want to go from that asymptote. So I'm going to go a few points to the left of that asymptote and a few points to the right of that asymptote. And depending on what the curve looks like, you may need to plot a few more points to get a better idea of our curve. And we got a bit of a wonky looking curve here, but when I plug in my points, I can graph a few points here, and this is what our curve is eventually going to look like. All right, second example, we've got x squared minus x minus 6 all over x plus 1. Same thing, we want to factor first. Every single time we want to see what we can factor before we get going here. So I'm going to factor the numerator into x minus 3 and x plus 2, and the denominator stays the same. We're going to identify our vertical asymptotes, again by setting the denominator equal to 0, and we'll go ahead and get x is equal to -1 again. Now let's take a look at our horizontal asymptotes. The degree of the numerator is 2, degree of the denominator is 1. 2 is greater than 1. However, 1 plus 1 equals 2, right? So 2 is greater than 1 by exactly 1. So we don't have any horizontal asymptotes, but we do have an oblique asymptote, right? So in order to find that oblique or slant asymptote, we can refer to it either way. We need to take the quotient of our function here, okay? And so let's see, we'll have an x first and then a -2. Again, I don't care about my remainder, all right? All I care about is my x minus 2. That is going to be the line that is my slant asymptote, right? So once you do this twice, right? Once you have 2 terms here in your quotient, you can just stop, all right? You don't care what that remainder is. You can stop here. That's going to be your slant asymptote. You can move on. All right, so if we go ahead and get our coordinate grid out and we go ahead and write out our asymptotes, okay, we've got x equals -1 here, and we've got f of x is equal to x minus 2 here. Okay, and then we can build our table, go ahead and plug in our x values, and we can find our f of x values, and this gives us our coordinate points, we can plug those in, and we get a curve that looks like this. All right, last example here. Again, we're going to start off by factoring. So I'm going to factor my numerator into x plus 5 and x minus 1. Notice here that I have a factor of x plus 5 both in the numerator and the denominator. What does that mean? That means we have a point discontinuity at x equals negative 5. And how did I get that? Again, whatever my factor is, I'm just going to set that equal to 0 and solve. Okay, that's how I get this point right here. That's how I get that point. So that's all I'm doing there to find my point discontinuity. So that means, do we have any vertical asymptotes? Well, it looked like we were going to have one here at x equals 5, or sorry, x equals negative 5. But since we can technically kind of cancel these out, right, I now no longer have any vertical asymptotes, as well as horizontal asymptotes, right? Because my simplified function, when I cancel out my x plus 5s, is going to just be x minus 1. So this might be a little bit hard to see, but if you take a look at both of the graphs for this original function as well as the simplified function, you can see that it is the exact same line. Okay, the original function is in red, and then right over the top of it is the simplified function, and that is in a dashed blue line, and that is the same line. All right, so we can just go ahead and graph the simplified function. However, be careful, because we do have this point discontinuity, which we can write as a hole in our graph just like this at x equals negative 5. Now, be careful, because one mistake that you may make, that a lot of students make, is you might check with your calculator what this looks like. Now, with your calculator, if you plug this into your calculator, this is our function, you are not going to see any point discontinuities on your calculator. Okay, that is just because of the amount of pixels that your screen has on your calculator. It's just the best that they can do. All right, so don't be fooled if you graph this in your calculator and it looks like this is a continuous function. It is not. You actually have a point discontinuity at negative 5, so you need to understand that when you graph and give your final answer if you were asked to graph a radical function. All right, so that is all that I have for you guys today. Good luck with your practice.